Have you ever wished an AI could know your business? I don't mean the public internet. I mean your private reports, your specific research, your data. Well, today, that's exactly what we're going to talk about. We are going to build a custom private library for an AI's brain, and we're going to do it step by step. So let's dive in.
Okay, so here's the big problem we're all facing. These incredibly powerful AI models we use, they're basically stuck in the past. They have a knowledge cutoff date, and even more important, they have absolutely no clue about your world, your company's internal reports, your personal research, none of it. So the question is, how do we fix that? How do we bridge that knowledge gap?
And the answer, it's this really clever technique called Retrieval-Augmented Generation, or RAG for short. To put it simply, RAG gives an AI the ability to look things up in a private library of information before it even tries to answer your question. It's the bridge that connects the AI's vast general intelligence to your specific private data, and that is a real game changer.
All right, so here's our game plan. We've just touched on the AI's knowledge problem. Now we're going to spend our time on the very first part of the solution, how we actually build that custom library. This whole process is called the Data Ingestion Pipeline, and trust me, it is the foundation for everything that comes next. Think of the data ingestion pipeline like this. It's the blueprint, the step-by-step assembly line for creating the AI's personal knowledge base. It's how we take what is often a messy pile of random documents and turn it into a structured, searchable memory that the AI can actually work with.
And here are the 4 fundamental steps on that assembly line. It's actually pretty straightforward. First, we load the data from all our different files. Then we chunk it, breaking it into smaller, more manageable pieces. Next, we embed those pieces, which is a fancy way of saying we turn them into numbers. And finally, we store all those numbers in a special kind of database. We're going to walk through each one right now.
Okay, first up, standardizing the information. Let's be real, our knowledge is usually scattered all over the place, right? It's in all these different unorganized file formats, and our very first job is to bring some order to that chaos. I mean, just think about it. You've probably got PDFs, websites, plain text files, spreadsheets, maybe even stuff in a database. The initial challenge is just being able to read all of these different types. To do that, we use these handy tools called loaders, and each one is a specialist at parsing a specific file type and just pulling out the raw text.
So once we've loaded all that text, we can't just leave it as a jumbled mess of words. We need one single, consistent format for everything. And that's where this idea of a document structure comes in. It's our standard way of organizing the text, and importantly, its context, no matter which file it originally came from.
Now, this standard structure has 2 really important parts. You got the page content, which is, the actual text itself, that's the what. And then you have the metadata, which is all the context, that's the where. This includes stuff like the original file name, the page number, maybe even the author. And this metadata, it's absolutely crucial. It's what lets us trace any answer the AI gives us all the way back to the exact source document.
All right, so all of our information is now standardized and neat. What's next? Well, now we have to actually prepare it for the AI's brain. This next phase involves 2 key processes. First, breaking the text into smaller pieces, and second, translating it into the only language an AI truly gets. And that language is numbers.
And this brings up a really good question, one you might be asking yourself right now. Why all this work? Why do we have to split everything up into these little chunks? Why can't we just feed a whole 100-page report into the system all at once?
Well, the answer is pretty simple. AI models have what's called a fixed context size. You could just think of it as a limited attention span. They can only process a certain amount of information at any given time. So by breaking our big documents into smaller, more focused chunks, we make sure that each piece can actually fit within that limit. We're making it digestible for the AI. So we have all these little text chunks. What do we do with them? Well, this is where the real magic happens. It's a process called embedding. We use a special AI model to convert each and every chunk of text into a long list of numbers. We call that list a vector. And this vector isn't random. It's like a numerical fingerprint that perfectly captures the semantic meaning of that text. This shows you exactly what that transformation looks like. A piece of text goes in, and this vector, this list of numbers, comes out. The best way to think about this vector is as a coordinate, like a precise address on a giant invisible map of meaning. Text chunks that mean similar things will have addresses that are really close to each other on this map, and that is going to be super important for searching later. And just to give you a concrete example, a very common and efficient embedding model called All-Many-LM L6 v2 we'll turn every single text chunk into a vector with 384 numbers, or dimensions. That's a very, very specific address for the meaning of that chunk. We are on the final step of building our library. We've standardized our documents, we've chunked them up, and we've turned them into these meaningful numerical vectors. So now we need a place to put all of them, and we need a way to search through them like really, really fast.
This is where the vector database comes in. And listen, this is not your typical database that just looks for exact keyword matches. No, this thing is purpose-built to handle these super long, high-dimensional vectors and to perform searches based on their position in that map of meaning we just talked about.
And that brings us to its superpower, similarity search. See, when you ask a question, we do the same embedding process to your question. We turn it into a vector too. The vector database then zips through all the vectors it has stored and finds the ones that are closest to your question's vector on that map of meaning. It finds the most conceptually similar information, even if the words you used are completely different. It's search by meaning, not just by keywords.
So let's just step back for a second and look at what we've actually accomplished here. We started with this messy, disconnected pile of files, and through this very precise process, we've built a highly structured, super fast, searchable knowledge base for our AI.
Here's that whole how it's made journey all in one place. We took the raw files and loaded them. We standardized everything into a consistent document structure. We split those into manageable chunks. Then we converted those chunks into meaningful numerical embeddings. And finally, we stored all of it in a searchable vector database.
And that's it. We have successfully built the AI's external brain. It's a custom knowledge library filled with our private information, indexed entirely by meaning, and it's all ready to be queried. The foundation for a truly intelligent, context-aware system is now officially in place.
Which of course leaves us with one final, very important question. The library is built, the books are on the shelves, and it's all beautifully organized. But when a question comes in, how does the AI actually walk into that library, find the exact right book, and read the relevant page? Well, that process is called retrieval, and it's exactly what we'll be covering next. Thanks for tuning in.